let's just take the time to present the problem of isometric embedding. So we consider a Riemann manifold given by a set of charts and the metric. And under which condition is it possible to build an isometric embedding? So isometric embedding means we can't stretch chart to glue it, and we want to know when is it possible to glue all these charts to build the manifold. So precisely, does it exist a map F? So from our Riemannian manifold to an Euclidean space of dimension n, such that for any curve in the initial map, then we have the length of the curve in the initial map, the length so for the metric G, is equal to the length of the image of this curve by the map F. So in the same way, we could say that we're looking F such that the initial metric equals to the pullback of the target metric by the map F. So we are looking for this map. And this problem in a coordinate system, write like it. So we write the metric G in coordinate ij, and we want to be this metric at the left equals to the metric at the right, which is given by the scalar product here of the partial derivative of the map F. So here I wrote only the two first row and line. So this is in fact the case of surfaces. And we see, of course, this matrix is symmetric. That means we have just n plus 1 over 2 equation to solve. So this is the equation, Gij equal to the scalar product of the derivative in the direction dij. And in 1926-27, there is the first result from Janet Cartan saying, yes, it's possible locally. So any analytical Riemannian manifold of dimension n can be locally isometrically embedded in a space of the dimension which equals to the number of conditions we have to satisfy the isometric constraints. So if we just have an overview of what's happened, so we have the problem of, so Riemann introduced an idea at the origin of Riemannian manifold in 1854. And then there is a problem of isometric embedding. So following his idea, when it's possible to build such a surfaces. And we have the first result in 26-27 we saw for Janet Cartan, which is only a local result. And if we continue in the history, we have after the Whitney theorem. The Whitney theorem is in fact about only manifold, not Riemannian manifold. So he doesn't consider the metric. And without considering the metric, just the chart, we can build smoothly manifold of dimension n and embed it in a space of dimension 2r. So we have this, and the global problem resist until the earlier of the 50 at the MIT, where there is a mathematician, Nash, and this mathematician is really confident, maybe a bit too much, and he annoys other people. And at one time, one of his colleagues proposed a bet. So, hey, Nash, if you're so good at one time, why don't you solve the embedding problem for manifold? So Nash started to work on this problem, and finally, just some years later, he managed to have these two theorems. One theorem in the case of the C1 regularity, one theorem in the smooth regularity. So the first theorem is the following for C1 regularity. So we consider at the beginning an initial map, which is strictly short, so where all the lengths are too short. And we say if all the lengths are too short, then we could increase it until have an isometric embedding, which is only C1, alas, but it's in codimension. So Nash say in codimension 2, and Kuiper improve it in codimension 1 year after. And this new map is as close as we want at the initial map. And the other theorem, so for smooth isometric embedding, stated for a compact manifold of dimension n. And here we see that we have a smooth regularity, while the dimension is really, really fragile. So in the following, we will focus on the first theorem, which could be proven using convex integration. So we take the first theorem. And in the first theorem, let's first ask the following question. Why can we have no more than the C1 regularity? Why not? Or just that? What's happening? So is it really possible, in fact, in regularity C2? And for example, this theorem, which says that there doesn't exist a C2 isometric immersion of a flat torus in dimension 3. Okay, so let's try to prove this theorem. And okay, let's assume that such a map exists. We can embed a flat torus in R3 with a regularity C2. So okay, we assume that exists. We have a surface. I don't know what it looks like. And what do we know? We know that, okay, a flat torus, well, it's just a part of the plane, it's a curvature equal to 0. And here, we have a complex surface. That means we could put this surface into a sphere, reduce the sphere until have a contact point here in red. So that means, in fact, the curvature is greater than the curvature of the sphere. That means the curvature is greater than 1 over r squared. And in fact, in this case, this is the following theorem stated by Gauss. We say that the curvature is preserved by C2 isometric map. That means that the curvature which equals to 0 here, but here it can't be equal to 0, it's strictly greater than 0, so it's impossible. So we are a contradiction in this case, so it's not possible to have a C2 isometric immersion of the flat torus in R4. Is it fine? Yeah. So let's continue a bit the historical part of the Nash-Kuiper theorem. So now we have the C1 isometric embedding of Nash-Kuiper. And in fact, this theorem was one of the inspirations for the convex integration theory for Gromov. And let's continue a bit what happened after. So, like I say, it's possible in C1, it's not possible in C2. So people are interested by the older regularity C1 alpha of such embedding. So in okay, so Conti de Lelis and Zekelidi prove that it's possible to have the regularity until okay, 1 plus the dimension, I guess n is the dimension of my manifold. So 1 plus n squared power minus 1. And we have also a first explicit construction of such an isometric map by the Debian team, which reveals the C1 structure. So when I say isometric embedding, here we see the flat torus is centered on this map. And on the flat torus, for example, we have these two black lines for the same length. And here, in fact, the black curve maybe it's a bit short. So this is a kind of star here and the big equator for the same length. And the two blue diagonal are the same length also here. So this surface looks like it. So if the historical part is fine, now we'll see the idea to build such isometric embedding. So the idea is the following. So if we increase length in one direction, okay, using corrugation, for example, we also modify length in the other direction. So we increase length in the direction, we have an error, we increase length in other direction, but we also perturb the first step. So we have to do it again. We can't reach direct geometry because we have an error in the form of a big O of 1 over n we saw previously in the previous talk. So the Nash idea is the following to control the error. Okay, we have an error. Well, we will increase the metric step by step and take the limit. Like if we have an error, and the error will decrease at each step and at the limit, the error go to 0. So in fact, let's take a look at the choice of Nash for the sequence of metric. So we have an initial metric, let's say G0, which is given by the strictly short embedding we choose at the beginning, and we want to modify, and G infinite, the metric to reach. So we have this isometric default. So this is the length we have to add at the end. And in the compact case, Nash shows this sequence of metrics. So he takes the metric G0, the initial metric, and he increases the length for the half of what we need to do, and again the half of its need, so now the quarter, and again, and at the end, at the limit, he reaches the metric we want to have. So in fact, this sequence satisfies the following constraints. So okay, the sequence, the limit of the sequence is the metric we want to reach, of course. At each step, the difference is positive, because at each step we can only increase length with correlation. We can't remove length, so we have to only have a positive. We need this difference is positive because it controls the length we add at each step. And we need also that this condition of the sequence, that means the sequence converge at the enough fast. And why we need that? This condition, in fact, will ensure at the end the C1 convergence of our sequence of surfaces, because this convergence allows to control the convergence of the differential. Because here it's encoded the length we need to add, and the length we need to add is encoded by the derivative, the partial derivative of surfaces. So let's take a look at the relation of isometric map. So we have to consider the error we accept at each step. So let's take an error epsilon k, and let's take a look at this thickening of the relation of isometric map for surfaces. So for surfaces, we are looking for all tuples that the scalar product of Vy Vj, which replaces the partial derivative, satisfies this constraint. So the difference with the metric is lower than epsilon k. And what is the slice? Okay, let's take a look at the slice in the direction d1. So we are looking for all the values that could take the first partial derivative, means we have a condition on the norm of the partial derivative, and a condition on the scalar product between the first partial derivative and the other partial derivative. So the first one is the sphere here for surfaces, and the second one is just the plane up of the sphere. So this slice of the relation is the intersection of these two conditions. So we see that it's a cycle. In fact, like we thicken the relation, it's a thickening of this cycle, which is this kind of torus, this thickening of the torus. So to the sequence of metric we choose at the beginning, in fact, this choice induces a sequence of thickening relation. So the thickening relation looks like it because we increase a bit the metric here, and we increase again the metric here, but we reduce the error. So we have, in fact, circle where the radius increase, but when the thickening decrease until the wanted relation here in black. Is it fine? Okay, so let's try in one dimension for curves. So here I just forget a bit the error, the thickening. So the slice for isometric map for curves is given by all partial derivative, so that the norm of this partial derivative equals something given by the intermediary metric. So the slice is the circle here of radius R1, and we have to take a loop which belongs to the slice and whose average equals to the derivative we want to modify. So here it's an arc of cycle. And we could choose this size of circle. So the radius is controlled by the length we need to reach, and the angle of the arc of cycle is constrained by the average we have to reach. And after in the direction of the derivative, we want to modify. So in the following, each time I will talk about corrugation in the isometric case, think about corrugation given by an arc of cycle. Maybe I will write it somewhere. Didn't forget. So let's keep that somewhere and let's continue. And note that if F0 prime is outside the circle, there is no loop which satisfies your constraint. That means if F0 is outside, the lengths are already too big, and we can't reduce the length using corrugation. So maybe again, a note. So like the slice is this circle, we see that the convex hull is the disk, so it's not ample. So here today we consider not ample relation. So we continue with the idea of Nash, which is increase length step by step. So we start by, for example, a cycle of length 1/2. We increase a bit, so reducing by the half. For example, if we want to reach 1/2 plus the difference. So we start by that, plus the half of this, so this is 1/4. So this is the second step, and we continue again 1/a plus, at the limit we obtain 1. In the case of curves. So okay, we understand. Is it fine for curves? We go to surfaces after.
But a question. So for curves, you could actually get it smooth, but still this doesn't converge to something smooth, or does it? Like, do you get more convergence in this case?
So yes, yeah, for curves it's tricky because if you want your derivative equal to something, you just have to take the integral.
Right.
So yeah, it's easier for curves.
No, but I mean, you still, if you want to C0 approximate the original embedding, you still have to do some corrugation, but you could do it in one step, actually be asymmetric, be C infinity smooth.
So I would like to say yes because Gromov formula allow it, but when you for people, I just recall a Gromov formula. So you start somewhere, you just follow the integral you need to do. If you want the really tricky curves, so for example, you take a closed curve, you do corrugation, but for Gromov formula, you don't know why you finish. So for example, if you have a closed curve at the beginning, you're not sure you have a closed curve at the end. So for example, if you want to have a quotient for an action group, I don't know why it's with Gromov formula. But yeah, it's closed. It's epsilon closed, but it's not a closed.
I think you can do some sort of implicit function, like you do many perturbations to call.
Yeah, after you have to add an interpolation and so it's a bit ugly to have the gluing. It's possible. It's harder. But yeah, it's possible for Gavi. Just a tiny example to understand the mistake.
Sure.
For sure. Okay. So let's go and let's consider for this the torus. So we take the standard parametrization of the torus. So we look at the isometric default of the first step. So the first step, we have an intermediary metric G1 to reach. And the difference is, of course, positive to have a length to add, which is positive. So we have something like that. So I will call that maybe. just recall that in a 2-dimension, the metric is of this form. So the isometric default is a symmetric matrix of size 2 times 2. And this, in fact, we rewrite the isometric default like a sum of square of linear form with positive coefficients eta I. So we want this coefficient are positive because they control the length of the corrugation. So we can't have a length negative one. And so we do see such a decomposition, but this decomposition is not unique. We have to choose one. So we choose one. And after, we have corrugation in this 3 direction. So the direction the x associated to the first linear form, the direction the x plus 2dy, the direction the x minus 2dy, to reach the metric G1.
Melanie,
Yeah.
why do you choose? I mean, why these directions and not I don't know x, y, and then a mixed one or something?
So your question is just why you just do 2?
No, but you're doing 3, no? No, anyway.
Yeah. So yeah. So can I say? So if we look at the isometric default, this minus another metric, which is 0, is also metric which is symmetric. So technically, if you have a symmetric matrix, you take the diagonalization, you could have only 2 directions. So yes, it's possible, and it's the case people in analysis used to increase the order regularity for isometric embedding. So they reduce the number of steps here, but in fact, in this case, we want to use these 3 directions at each step. So for G1, G2, G3, and again, to have a fractal behavior after later. So for an explicit construction, it's better to keep, in fact, the parameter at each step. So it's really a choice to have 3. Okay. So technically, it's possible to have 2, but you can't if we choose this only 2. Say DL1 square. We don't know if at the next step it will be the same linear form.
Yeah,
so for an explicit construction, you just put something explicit here. See, it's possible. So we continue. So for each intermediary metric, we have 3 steps. So 3 steps for an explicit construction. Thank you. So iterating and passing at the limit, we obtain, following the Nash idea, a C1 isometric surfaces. And just let's take a look at this C1 isometric surfaces. So in fact, this surface seems to be self-similar because we had at each step corrugation. So if we zoom, we see corrugation. We zoom a first step, we see again corrugation, and again, and again, and again. So we have the feeling that this something has happened, which look like a fractal behavior, but a fractal, in fact, can be C1. So something happened, we want to understand that. And for that, we will look at the normal map. So let's go back in the case of the curve, and let's check the normal map, the behavior of the normal map in 1 dimension. So the normal map is given by that. I need to repeat it, maybe not. So this is exponential of I of a sum, and this sum, in fact, in this sum, the alpha k is the angle of the arc of cycle we choose at each step. So we have the sum of the angle of the arc of cycle at each step, goes to pi, the number of corrugation at each step, which controls the error. So like the error reduced, the number of corrugation is big and big and big at each step, times the tangent vector at the beginning. So what's happened in this big parenthesis? In fact, this looks like Weierstrass function. So here, Weierstrass function. And again, we give you the usual definition. So I don't know if that helps. So usually we express function right like it. So the sum for I choose n. Yeah, it's a parameter power n plus something bn x with the condition greater than 1. And in fact, this family of functions are continuous, but nowhere derivable. So it's really no like a kind of function for the fractal behavior. So here we see a fractal behavior not on the curve itself, but on the normal map. And we would like to check the same for surfaces. We would like to check the normal map with C1 isometric surfaces. So we didn't do that for the torus. So we will consider another surface. In fact, we will consider now the hyperbolic plane. So what I call hyperbolic plane here, I consider the model of the Poincaré disk. So I recall here what is the Poincaré disk. Here is the metric H. So for the metric of the Poincaré disk, in fact, each blue triangle has the same size for this metric, but of course not for the Euclidean metric, which is at the border the size reduced. So if we follow the idea of Nash, to have an embedding, we have to increase length on the edge to reach an isometric metric. So once again, we know that it's not possible to do such isometric immersion in situ regularity thanks of the theorem of Hilbert and Efimov. So there is no situ isometric embedding of the hyperbolic plane in dimension 3. But it's possible with the theorem of Nash. And we did an explicit construction in a joint work with the EVA team, so that, in fact, we build such an embedding with a condition with the infinite boundary, sorry, a property on the infinite boundary, where the curve of, on the border, infinite border of the disk is of order dimension equals to 1. And this explicit construction looks like it. So again, usually we are epsilon close to the initial surfaces. So here we see that in fact the initial surfaces is not the disk, but for explicit construction we choose the down part of a parabola to have a nicer parameter. So we choose this kind of surfaces, and we have corrugation. And we see that of course the corrugation are more on the boundary because it's there we want to increase the length in particular, so the initial surfaces were 1. And we increase length more on the boundary than at the center. And we want to look the normal map. So we want to look the normal map. We take a little arc of cycle there, close to the border, and we have the normal map. The normal map so belongs to the unit sphere. So here we have the unit sphere, and here we have the image of the normal map on the little arc of cycle in a range I draw on the blackboard. And it looks like it after 5 steps of corrugation, and it looks like it after 6 steps of corrugation. So we see that more we corrugated, more the normal map do a mess on the unit sphere. And in fact, we see, if we focus on what happens, we see a repetition of the same shape, which is in fact, we can prove a property of self-similarity. That means this is a pattern which repeats. So we have a pattern in red, which repeats in a pattern in orange, and green. So we don't really have this feeling on the picture because there's also a rotation on the pattern on the unit sphere. But there's really a self-similar property on it. And here we are really, really close to the boundary. We are at a radius 0.9. So the fractal, well, say the self-similar property is on the normal map and not on the surface itself. This question, oh, it's fine. And I would like also do a link with another way to use the Nash idea, but in the Monge-Ampère equation, well, in fact, in a weak version of Monge-Ampère. So it's a result of Marta Lewicka and Reza Paxat. So they consider a weak version of the Monge-Ampère equation, mean usually the Monge-Ampère equation if for partial derivative or for the two. So they took a weak version in order one. So they are looking for V and F is the data here. So imagine F is the metric we want to reach. So it's the data, they want to reach that. So they modify also the return of the constraint to something else. So now the data become a big A. And they are looking a couple of functions, VW. And they use the same idea as Nash. They can't reach in one step the data, A, but they could cut step by step with an error and control the error at the end. So they compute, like in the isometric case, a default. They call a deficit. So what they want to reach minus what they have at the previous step. And they increase little by little. And in this case, in fact, the slice of the relation is not a Markov cycle, but I guess it's all the parabola. Yeah. So it's not amplitude. And it's closed also. And they managed to do one also in regularity only C1. So for this result, they also did some explicit visualization. And we saw that there is an initial surface. Well, I don't know if it's a surface for them. And they had corrugation step by step. And this looks like a bit what you saw, an iteration of corrugation. And I put after the references at the end if you are more interested. Thank you.
Are any questions for the speaker?
Melanie, can you say more? So if you had like what you said earlier, like you only do 2 perturbations. You said, I mean, it's better to have less because like there's you control the errors and you get better regularity.
For the good regularity, yes. But it's a bit tricky because you could take the diagonal of the isometric default, but is it possible to take the diagonalization in the same coordinates over all the surfaces? So Nash don't go in this when he just says this is a boundary, and he says this is an infinite step, we say an infinite number of directions, while we have to correct the isometric default. The why we do that in this kind of decomposition for direction is, in fact, I have to do it again. So yesterday we saw that we could just solve in each direction, and we don't care for an open relation. But in fact, here we have the next step in more direction, or I really drive really bad methods. Okay, so this is the relation at one step, and the next step, the metric is higher, but the default is really little. So okay, we could solve this relation just modifying partial derivative by partial derivative. But if we are here for the next step, we have a problem because we need to be in the convex hull of the next step. So in fact, there's an additional constraint for direction to be sure we are in the convex hull of the next relation.
It is not a real H principle. The relations isometric.
So this principle say let's try the usual H principle, which is like, okay, you take a formal solution. You could modify it to obtain a polynomial one. And in fact, in this case, like it's not ample, we had to add a constraint, a formal solution, plus being in the convex hull. So here it's the length is too short. The length is too short means we are in the cycle. So we need that all the lengths are already short. So in the compact case, it's fine because you just take the surfaces and you multiply by a little number to shrink it. So in compact case, it's fine because any formal solution you could shrink in to be short. For non-compact case, it's more tricky.
In the compact case, also you have more complicated targets, and there might be an obstruction depending on how much of the class you want your mapping. No?
I don't know exactly what it means.
Well, you know, Melly's saying you can always take any map into Rn and make it short by shrinking it, but that's because Rn, you know, you can shrink it. But if you are in some manifold with topology, you might not be able to just shrink any given map to make it short. So,
One question, I forget, when you corrugate, if you take big N sufficiently large, is the result C1 close to the initial? I'm wondering why corrugating an initial embedding remains an embedding.
So yeah, it's a good question. So we can't choose any kind of corrugation because we choose corrugating with self-intersection. So we really have to choose the good corrugation who has no self-intersection. And where's my so usually we have this kind of corrugation, and so the how can I say? Kuiper do it in codimension 2. So to avoid self-intersection, he had an helix. So they adding helix and doing in a little neighbor. He saw that he will say an embedding because he does that. If at the beginning it's an embedding, he could do in a little neighbor of the initial embedding, and helix never cross. And in fact, so this is in codimension 2, and Kuiper managed to write a corrugation who also have never intersection with the amplitude. So it's a, I would like to say like a graph, because when you have a graph, you can't have an intersection. So it's a rewriting of corrugation given by Kuiper to improve this result.
Okay, so you definitely don't get something C1 close, but this is why it works.
So yeah.
Thank you.
So, yeah, so the embedding condition, it's not seen in the differential relation, so we have to control the error in the C0 closeness at this time. Indeed, yeah, thanks.
Well, if there are no further questions, let's thank Melanie again.
It's